Okay, this video is going to go through Unit 3, Lesson 4 of AP Calculus AB. This is curve sketching. So we're going to use what we've learned in the first 3 lessons, taking first and second derivatives, and applying that to sketching a pretty accurate curve without a calculator and getting all the important information in that graph. Okay? Just so you guys know, I've also posted these filled in notes. So if there are parts of what I discuss going forward that are unclear, or if you want to skip ahead and just look at maybe answers and not watch the whole video, you've got those posted as well. Okay? And it's pretty windy and rainy right now as I'm making these notes, so I've got some night jazz going on. I hope the music doesn't distract you too much. Okay, let's get into this. So what we've got first in this first example is a walkthrough of really these 9 steps that we need to complete in order to sketch a graph. Okay, so this is a cubic. You know, we could probably get a pretty accurate sketch of this just from our general understanding of polynomials, but we're going to go into more detail and see how that can be improved on when we use derivatives. Okay, step 1, find the domain. For what values is f of x defined? This is a cubic. It's a polynomial. There are no places where it's undefined. So the first step of this is pretty easy. The domain of this is all real numbers. Okay, so there's no x values that we have to exclude. Find and name any discontinuities. Do we have any holes, vertical asymptotes, or jumps? Well, if the domain is everything, we don't have any discontinuities. Okay? But this is always something that you want to look for as you complete a curve sketch. End behavior. We want to describe end behavior using these 2 limits. Okay, and then you know, sometimes end behavior can indicate a horizontal asymptote. So if there are any of those, we want to indicate that. Again, this is a cubic. The leading coefficient is positive. So this graph, you know, is going to look, who knows what's going on in the middle, but it's going to be looking like that end behavior wise. Okay, so we can say and write that the limit as x goes to infinity to this function f of x is going to equal positive infinity, or just infinity, right? I don't really need to write the positive there, so right. So as this graph continues to go to the right, the y value is going to go up and up. All right, and the left end behavior is going to do the opposite. So as x goes to negative infinity, the function values of f of x are going to go to negative infinity. Right, so that means that as we keep going left, the y values will keep decreasing and decreasing and getting more negative. Okay? So that's it for this page, or this part of this page. Let me check all these 3, and we'll scroll down. Find easy, right? Easy, keyword being easy, intercepts. So really that means y-intercept, and then any zeros that we can get if we factor. Okay, so we're pretty lucky. We've got 2 x-intercepts here. And we know, hopefully we know from last year that this is a bounce, so it's going to bounce at x equals 2. Okay? So let me get this black pen that I want, and I'll say x-ints. So we have 2, 0, which will be a bounce. And the other one was negative 1. Okay, and then the y-intercept, we can just plug in 0 in our equation. So this will be negative 2 squared, which is 4, times 1. So the y-intercept will be 4. So I'll list that too. The y-intercept is going to be 0, 4. Complete a sign analysis of f of x. Determine the intervals where the function is increasing and or decreasing. Okay, so this is basically the first derivative in the number line. All right, And what I'm going to do is I'm going to put those number lines, I'm going to draw them, but then I'm going to copy them down here because I want to put them really right above and below each other, so you'll see why. Okay, so let me be kind of type A and thorough here and check off that step 4 is done. Okay, so now we do first derivative analysis, and I'm going to recopy what our function was. So f of x was equal to x minus 2 quantity squared times x plus 1. And then if we take the derivative, so f prime of x, well, this is going to be product rule. So the way I do product rule is I copy the first, I take the derivative of the second, and then I copy the second and take the derivative of the first. Okay, so here's my first, 1 is the derivative of the second, here I've copied the second, and 2 times x minus 2 to the first times 1 is the derivative of the first. Okay, I want to get this in factored form ideally so I can make it easy to analyze. So this is equal to x minus 2 quantity squared plus 2 x plus 1 x minus 2. Okay, and then if I factor this, this becomes x minus 2. That can come out. Okay, then I've got, let me make a bracket here just to make it a little bit more clear. So I've got an x minus 2, right? That's the other x minus 2 that's left when I factor one of them out. And then I have plus 2 times x plus 1. Okay, so that's the part here that's left when I factor this x minus 2 out. Alright, almost there. So now this becomes, again, x minus 2, and now I'm going to combine everything. So x plus 2x is 3x, and minus 2 plus 2 times 1, that's negative 2 plus 2, that's just 0. So this, I believe, is our first derivative. Okay, so then what I'm going to do is make a number line, make sure to label that it's f prime of x, and I'm going to label the points where this thing has zeros, right? So this thing's equal to 0 at 0 and at 2. Okay, and then if I do a sign chart, if I take a number left of 0, like negative 1, and I plug it in here, well, this will be negative, so the whole result will be positive. Okay, if I take a number between 0 and 2, like 1, this will be negative, this will be positive, the whole thing will be negative, the product will be negative. And then if I pick a number greater than 2, like 3, this will be positive, this will be positive, the product is positive. Okay? So I'm going to copy that later and put it next to the graph, but what this really tells us for now is that this thing is increasing when x is less than 0, and when x is bigger than 2, and it's decreasing when x is between 0 and 2. Okay? Check, and I don't like that check. I think I'm going to copy that right now, just while I'm thinking about it, so I need to make sure that I have enough room. So this, I want to copy this, and let's paste it. I might have to resize this thing. Well, let's see though. Paste it here, and then can I don't know if, okay, yeah, good, I can resize it, so I'll put it right there. Okay. Determine any relative mins or maxes. Well, here's where we can look at, again, our first derivative chart. If my first derivative goes from positive to negative, it means the graph itself is going from increasing to decreasing, so there's a max here. And if my derivative goes from negative to positive, it means that the graph is going from falling, decreasing to increasing, so there's a min here. Okay, so I'm going to write that there's a relative max at 0 something. We'll plug in that number in a second. Actually, we've already found it because we know it's the y-intercept. And we have a relative min at the point 2 comma something. Okay? Which, so look at this, we actually know both of these. 2, 0 is our bounce. Okay, so that's an x-intercept. And 0, 4 is our y-intercept. All right? Sign analysis of f double prime. Okay, so now we need to take the derivative of the derivative. So I'm going to choose this form of the derivative. Okay, and I'm going to write that because I think it's just easier to take a derivative when we don't have product rules. So the derivative is going to equal 3x squared minus 6x. Okay, how am I getting that? Well, all I'm doing, right, is I'm taking this form and I'm just distributing. 3x times x is 3x squared. 3x times negative 2 is negative 6x. Alright? Then, f double prime of x is just the derivative of this, so that's 6x minus 6. And that becomes, if we factor 6 out, 6 times the quantity x minus 1. Okay, so I know I've got one place where the second derivative is 0. Alright? So I'm going to, again, make a number line. I'm going to make sure that I label that. This is f double prime of x. And now, see, I want to line it up, so I'm actually going to make it 0 here. Okay, and same idea. If I pick a number, sorry, that is not correct. Glad I didn't go too far with this. It's going to be 1, which actually comes out to be pretty good visual-wise. Okay, so this is x equals 1. If I pick a number greater than 1, like 2, this will be positive, so the whole second derivative will be positive. And if I pick a number like 0, which is less than 1, this will be negative, this will be positive, the product will be negative. Okay? So that's a number line representing my, or sign chart representing my second derivative. And just while I'm thinking about it, I want to copy this. And I want to put it right below the first derivative, right? So I'm going to try and line them up. That looks pretty close. I'm going to make this a little bit larger. Well, okay, I guess that's gonna have to be how it goes, but good enough. All right. And now determine the concavity. Well, this is, sometimes a little bit confusing. Negative concavity, I'll label it here. So this means negative concavity means the graph is concave down. It's the same exact thing. Okay, and positive concavity means the graph is concave up. So concave down, can look something like this. Concave up looks something like this. All right? And, obviously this part, the graph is increasing concave down. This part, the graph is decreasing concave down. This part, the graph is decreasing concave up, etc. Okay? So we can say, to answer the question in 7, this is concave down for x less than 1, and it's concave up for x greater than 1. Okay? So we're getting close. Points of inflection. Well, remember, this means it's very similar to a relative max or min, but the principle is applied to second derivative. So my second derivative changes one place at x equals 1. It goes from negative to positive. Okay, so that's going to be a point of inflection. So we have a point of inflection at 1, and then if I go back to the original and plug in, well, when x is 1, this is going to be -1 squared, so that's just going to be 1. This is going to be 2. 1 times 2 is 2. Alright, that's done. And now, complete a careful sketch. Okay, so what am I going to do? I'm going to put in all my points first. Okay, so point of inflection at 1, 2. That's right there. Right? What else do we have? We had x-intercepts at 2 and -1, and a y-intercept at 4. So 2 and -1, 2 and -1, and a y-intercept at 4. Okay? And now, if I look at this graph, right, of the first and second derivative sign charts, right, what I'm going to do is try and make a piece of the graph at every place where either the first or second derivative changes. Okay. I'm just making sure that I have these. Yeah. Okay. Sorry. So, up until this point, 0, right? The graph is increasing, and it's concave down. So that portion of the graph will look something like this. Okay. So I know from that's going to be the shape from to the left of x equals 0. So the graph will look something like that. Okay, that'll be its shape. This part's done. The next kind of important point is 1. Right, that's where the second derivative changes. So, and the first, really. So now between 0 and 1, the graph is, the first derivative is negative, which means the graph is decreasing, so it's going to be decreasing, but it's still concave down. Okay, so that part of the graph will look something like this, right? It's decreasing and concave down until 1. So I'm going to try and draw that. Okay, decreasing and concave down. Right, this part's done. At x equals 1, now if we look at what's happened, the second derivative has changed, right? From 1 to 2, still the graph is decreasing, but it's concave up now. Okay, it's actually going to be concave up for the rest of time. So let me make another dotted blue line here and say that, okay, this is going to be the case for how this thing behaves from 1 to 2, right? So decreasing, but concave up. So decreasing but concave up looks something like this, okay? That's going to happen until 2. Oh, I had a little bit higher than 1, right there, okay? And then finally at 2, the first derivative changes. It goes from negative to positive. So now the first derivative is positive. That means the graph's going to be increasing, and it's still concave up. So that means the graph will look like this. Okay, we've done this. So our last kind of portion of the graph, we want it to be increasing and concave up. Done. All right. So that's a pretty accurate graph. You know, we have all the important points where either the first derivative or second derivative changes, and we also have, you know, like x, y intercepts and that. Okay? So I'm going to stop the video there, and then I'll make a second one if there's anything left. Yeah, there is. Okay? But this has been enough, so I will end this video right now.